All right, so today we're going to be looking at the physics concept of work. Um, really, what we're doing is this is kind of the next step after looking at force. It's essentially uh, like we can measure how much force we exert on an object. We can feel that force, like when I push against the wall, when I push against, a refrigerator as I move it across the floor. I can feel how much force is being exerted on my arms in those cases. So one of the things we could ask then is how much work is done to move that fridge? Really, we're looking at work and energy are kind of the same things. It gives us a way to kind of calculate each other. So starting off, we're just going to look at work. So two equations we're going to want for just starting off with here is we have work equals force times distance, and work equals force times distance times cosine of theta. So essentially, we're working with vectors still. Work has a direction with it. One of the big things about the F and the D here is to calculate work, the force we apply, we're only worried about the force that's being applied in the direction our distance is changing. So for the most things, if we're just talking about one-dimensional movement, force in that same direction, there's no problem. If, however, like I'm pushing horizontally, where this one comes into play, let's say I'm trying to push my refrigerator here. I push horizontally up it. It moves a certain distance, kind of at whatever angle that is. In this case, my force, all of my force isn't going into moving the refrigerator up the slope. Some of my force, as we know, is being directed into the slope there. So to figure out how much of it is in that direction, we just do cosine of this. Okay, that's going to figure out our proportion for us. So, but that one we're not going to worry about quite yet here. All right. So let's say I am working in a hospital. I have a 72 kilogram patient, 72 kilograms with a gurney. I apply a force on it, on the gurney that the patient's on. The gurney and patient accelerate 0.6 meters per second squared. And I apply this force, it accelerates for 2.5 meters. My question is, how much work is done here? How much, I'll even capitalize work is done. All right, so starting off with, I don't have force, okay? But they did give me mass and acceleration. And if you remember, to figure out force, force is just mass times acceleration. So let me get out my calculator here because it doesn't appear to be up. Calculator. All right, so the mass we said was 72 kilograms. Acceleration we said was 0.6. Looks like I'm using 43.2 newtons of force. I'm going to fill it in on my diagram here. All right, 43.2 newtons of force. So now I have force and I have distance. According to this base equation, I just need to take that force times the distance. So in this case, the force we said was 43.2 newtons. Distance we said was 2.5 meters. 43.2 times 2.5. 2.5. It looks like I did 108 units of work. So now I said energy, work, same thing. We haven't talked about energy yet. Really, the common unit that they came up with for work was the joule. 108 joules of work. Typically, that's how you're going to always see it. But if I look back, like newtons is actually kilograms per meter, kilogram meters per second squared. Like that's what a newton equaled. Well, now for work, if I'm looking at kind of those base things, if I'm taking force times distance, so I have kilogram meters per second squared times distance, which is in meters. The other unit I could see for this is kilogram meter squared per second squared, because that's rather than saying all of this, essentially physicists just said, yeah, let's just call that a joule and be done with it. And so they did, and everybody lived happily ever after. All right, so let's look at kind of a different example here. Let's look at it where I'm applying a force, but my distance is in a different direction. So in this case, let's say I have a piece of luggage. And let's say that my luggage is at, we're going to have a lot of luggage. It has a mass of 20 kilograms. And my luggage has a handle on it so that I can pull on the handle. So we're going to say my force that I'm applying. And let's even say that I'm applying 20 newtons of force. And we're going to say that we're applying that at, let's go 50 degrees, kind of above the horizontal. Okay, so 20 newtons diagonally, 50 degrees, at a 50-degree angle. Let's say my luggage, though, I'm applying that force. We're going to move it quite a ways. You know what? Let's just stick with 20 meters. I'm moving it through the airport. So now I'm still wondering how much work is done. So to do this, I could go through and I could do my force triangle, figure out my force, in the x direction, force in the y direction, blah, blah, blah. Or we can just use the other equation where force is equal to force times distance times the cosine of theta. Because essentially, the cosine of this angle here will tell me my force in the x direction. Because if my luggage is being accelerated in that direction, my distance was in that direction, that means not all of my 20 newtons of force is going in that direction. Some of it's going up. So now to figure out this one, I just need to plug these things in. So force we said was 20 newtons. Distance we said was 20 meters. Oh, in this case, I didn't even need the mass here. I give you the force there. Times by the cosine of 50. All right, let's see if this thing is working right. Let's go. Let's bring this over. Okay, 50 cosine times 20 newtons times 20 meters. All right, it looks like we are applying, bring that back up, 257.1 joules of work. So 257.1 joules of work. Really what we did is as soon as I took the cosine of 50 times the 20 newtons, that told me the force in the x direction. Essentially, when we're doing these problems, like we're not necessarily wanting to diagram every single force acting on these things. There are some times where we may need to do that, or where we may need to even think about how much work is fiction applying to an object. But we're going to talk about that next time, I believe. So with that, there are some practice problems, and good luck.